All right. We're going to talk a little bit about centripetal force. Okay, and so I want to sort of again frame this around some questions here. Um, and the first question is, why does it feel like you push against the car door, seatbelt, person next to you when the car turns? Right, your car turns left, and you kind of get like feel like you're getting pushed to the right. Okay, why do they bank and slope car ramps? So this could be like if you ever watch like a race, a NASCAR race, something like that. You can see most of the courses have banked ramps. You can also see it on exit ramps for highways. A lot of them are banked. Why are people waitless on the International Space Station? And what's the deal with these carnival rides? So we'll show you a really quick video of this. Um, if you want to, obviously, you can click the link and watch a little bit more. But it is a circular, it's a cylinder thing that spins, basically. You can see him sitting there as it speeds up. All right, we can skip ahead a little bit. It's still speeding up. Um, and where is it? Right here? Right here. You can see they're starting to, oh look, they're actually now just like standing on the wall. You can see their feet are not on the ground. How is that possible? Okay. All right, so those are the four kind of burning questions here, or starting questions, and we will go through those, and then we'll talk about what they sort of tell us. Then I got a couple examples at the end there. All right, so what happens when you turn in a car? Okay, so let's see what's happening. I'm going to draw a top-down view. Right, we've got a car. My cars are pretty bad, but let's say this is my car. Right, and if we're just kind of like, here's a wheel, right, there's the wheels, and we're kind of looking at it from the top down. So let's see, you've got you kind of sitting, let's put you right here. So I don't know how you draw this, but like you're sitting up person right here. Okay, and as the car turns, let's say left, it's going to turn left or whatever like that, you're going to feel like you're getting pushed against the wall. Feel like you are getting pushed that way. Okay, I'm going to call it what you feel. But what's actually happening? Okay, so you're not actually getting pushed against the wall. It's a common misconception. It feels like you are, but that's not actually what happens. All right, what's actually happening is that your velocity is this way, right? Your final velocity is this way. In between those, you need to have an acceleration that is pointing right perpendicular to this path. And that's what's going to get you to that final velocity direction. So that means there also has to be a force, right, that's pushing in the direction of this acceleration. And what's exerting that force from the acceleration, okay? Or exerting that force, right? There has to be a force, right? If we're thinking about F net equals ma, and that's equal to like this force, there has to be at least one force that's doing it, right? And that's the force of your seatbelt. Could be the force of car door, etc. Whatever it is pushing you that way. All right, so you're not actually getting pushed against it. What's actually happening is the car door is pushing you, or the seatbelt is pushing you in the direction that you're turning. Okay, so it feels like you're pushing against the next person, right? If you're sitting next to someone, you're pushing against them. They're pushing against you. All right, so it's a little bit counterintuitive. It doesn't quite match what we have happening. But if you actually think about what's happening in terms of a velocity point of view, that's what's happening. So when you turn in a car, right, the car exerts a force perpendicular to that motion, to your motion, right? That's how it works. That force, right, is exerted by the door, by seatbelt, by the person next to you, right? So there's some force there, and that's what's pushing you. And it only feels like we're pushing against them, but actually they're pushing against us. Okay. All right. I mean, really, both are happening, but it's like the reaction, Newton's third law, action and reaction force. But really, the action force is them pushing against you. Okay, so let's keep talking about this car, though. What about the car? Like, what happens when it turns to us? Now we're just talking about the car. Okay. So we've got our car again here, and it's again going to try and turn this way, right? So this is its velocity initial here, and this is its velocity final. It's going to try and turn. Okay, what happens if it turns too fast? Right? You've all seen a movie where someone like yanks the wheel all the way to the right. What happens? You spin out. Okay? So why does the car spin out sometimes, but sometimes it is able to turn? Well, let's look at it from a forward, like from the front. Okay? So, or actually maybe from the back, whatever, it doesn't really matter. Right? Here's our car. We're looking at it from the back. Right? There's the car. Got wheels coming out here, wheel here, right? There has to be a force sideways, right? Because again, the car has to have a force that way, right? We're having some force, right, that is pointing this way. Now, what can exert a force that way on the car? Well, the answer is the only force that can exert the force that way is the force of friction. So there's a force of friction between the tires and the car. And because in most cases, right, if the car doesn't slide, it's static friction. So, but if you turn, which means it has a maximum. So if you turn, try to turn too sharply, that you start to slide because there isn't enough friction. The frictional static friction force is not enough to make you turn that type of corner. So, why does this lead to banked curves? All right, so this is kind of cool. So why do we then bank curves on a racetrack here, right? So here's our banked curve. Our car, again, we're seeing the back of it here, or the front, whatever you want to say, right? It's coming up. Here's our car. These are the wheels, right? There it is. We got a little. I'm gonna be artistic today. We got a little tail light here. Right, a little tail light. Okay. It's got to have a force towards the center of this track. So there's actually this net force, right? We know it's accelerating in the circle. We know the acceleration is towards the middle, right? Okay. Right, because that's something, which means the net force is also towards the middle. Now, if you look at this, there's force of gravity down. There's normal force. Oops, that's not how I wanted to draw that. Oh, I erased part of my car. Disaster. There's a normal force, right, up perpendicular to there, and the frictional force is this way. Now you might say, like, whoa, well, how does that help? Now the friction force is at an angle. But the important part is the normal force is now helping. There's this component of the normal force, right? The normal force is made up of two components. And now there's a component of the normal force that's in the direction of the acceleration. So frictional force is now getting some help from the normal force. As you tilt it more and more and more, the normal force is taking over. And the normal force has a way higher maximum than the frictional force, right? Because, I mean, this is like a concrete thing, like, right? The car is not going to, it's way easier to skid a car across concrete than it is to, like, make it go through the concrete, right? We can all agree on that? Okay, so that's what's happening. So why do we make a curve? All right. The force, the net force, is still towards the center of the track. A banked curve turns the normal force at an angle, or a banked curve. So a component helps turn the car, right? This means it's no longer all on friction. It's now a little bit on the normal force. Okay. All right. Now, let's go a little bit away from cars here. Let's talk about the the International Space Station. So, first of all, just a simple fact. Gravitational acceleration is not 0 on the International Space Station. It's actually, I think it's 0.8 or 8.6 meters per second squared. Okay, that's like 88% of normal. All right. So why don't we feel it? So let's think about what's happening on the International Space Station. We've got Earth, right? And we've got International Space Station, and it is going around in this big circle here, right? And then we've got U, tiny little U, on the International Space Station. There's a force of gravity on the International Space Station. There's also a force of gravity on you, both pulling you down towards Earth, right? Has to be, okay? And we're close enough that's still significant. So why don't we feel it? Okay, so let's think about when actually you feel weight. Okay, we feel weight. What happens if you're falling? Do you feel weightless then? Do you feel weight? You don't feel it as much. When we say we feel weight, right? So weight is not 0 here, but when we talk about how you feel weight, it's actually the normal force. That's the feeling of weight. So you can have, so what I'm saying here is weight does not equal apparent weight. Okay? In other words, what it feels like you weigh. Okay? So on the International Space Station, you have weight. What you don't have is apparent weight. And that's actually probably more important for how you move around. Okay? All right? So what's happening, right, is that you have, in order to go in this circle, which you're going in, you have to have centripetal force, or, well, sorry. You have to have something towards the middle. Some force towards the middle, that's gravity, right? And that gravity is what's making your net force. You have a net, right, towards middle, Earth, right? Because the acceleration is towards the Earth. Right? Because the centripetal acceleration towards the Earth means the net force is towards the Earth. And Fg is what's causing that. Okay? Now, towards the center. Now, what this can be off by, right? If you do this wrong, right, you would still have the spaceship would also have to either help you or not help you to do that. But if you do it just right, which of course, obviously the International Space Station, because it's up there all the time, has to do it just right, it is perfectly moving around in this circle, and you're moving around inside of it at exactly where the force of gravity is the only force needed to keep it in exactly this circle. So inside of that, you are moving in this perfect circle inside the International Space Station, which is also moving in a perfect circle. And so you are not being held up or held down by the International Space Station. So you don't feel weight because there's no normal force keeping you there. All right, so finally we bring ourselves to these carnival rides, the ones we just showed. Okay, so in this carnival ride, right, if we want to look at it from the side, it's basically just a barrel, and you are up on the side there, stuck to the side. Okay. Now let's think about the forces that act on this. You've got the force of gravity, right? That's downward, but you don't seem to be moving downward. You seem to be moving in a circle, which actually means that the F net is towards this way. Right? I don't like to, I'm going to do a different color because I don't really like saying F net's that way. But what actual force could be that way? Well, you're in contact with the wall, And then what keeps you from falling down? Turns out it's actually friction, keeping you from falling down. So we actually have this force of the wall, right? Because it's the normal force. Centripetal force is not a force, but this force of the wall is the normal force. Okay. The force making you move in a circle is caused by the wall and is a normal force. And because it's a normal force, right? Because it's a normal force, we get friction. And that friction is what's able to oppose gravity pulling you down. Okay, so what do we know about centripetal force? First of all, it's not a force. It should never be listed on a force diagram. I sort of did that here, but it's not a force. Okay? Centripetal force is a term for what happens when you move in a circle. It's not the force that does it. It's what makes you move in a circle. It is the net force. It is a specific net force whenever you're moving in a circular motion. Okay? And because it's net force, you shouldn't draw it on a force diagram. And therefore, when an object is experiencing uniform circular motion, Fc is not on the force diagram. Okay, it's not there. Okay. But it's always, so that means the net force, and because Fc, right, is a net force, it's equal to mass times acceleration, and this is the acceleration, right? The centripetal acceleration, we get mass times v squared over r. And this is towards the center of the circle. So, make it sum up, when you're moving in a perfect circle, F net equals mv squared over r when experiencing uniform circular motion. This uniform just means v is constant. Okay, everything else is done. All right, so let's do some examples with this information. First one, we've got a bike riding around a quarter-mile flat circular track at 20 meters per second. What is the minimum coefficient of friction between the biker and the ground? I guess the biker and the track maybe is the bike and the track is really what we're looking for here. Okay, so let's look at it from the side perspective. We got, here's the ground. All right, we got the bike, right? It's like a, there's the bike. Got a person on it. Right, we're doing this. They are turning. So we've got a force. We got F net here, or Fg down, Fn up, and we know that there's some sort of force, right? The net force, the acceleration's this way, and we know that there has to be a force then in that direction, right? At least one. And so it's actually, we can say it's the force of friction between the tire and the ground. So, F net horizontal is equal to the force of friction, which is M A centripetal is equal to the force of friction, which means mv squared over r is equal to the normal force times yes. And the reason I'm able to say this minimum means, right, so first of all, it's static friction. Static because no sliding. We don't want our tires to slide on the ground, right? Okay. And the force of friction is we're asking for the minimum coefficient, which means I want the maximum. So this is really Fs max. Okay. So mv squared over r equals normal force times coefficient of static friction. Okay, so we've got a bunch of this information. Mass, right? V squared. It's 20 squared, so it's 400. R, it's a quarter mile flat track. I guess I should have to do a conversion here. A quarter mile is 400 meters. So the circumference, 400 meters, which means that 400 equals 2 pi r. R is 63.7 meters. The R is 63.7, so this is over 63.7. And then we have normal force. Oh wait, we actually have F net vertical, and this is equal to Fn minus Fg. And we know the acceleration vertically is 0. So this becomes Fn minus Fg. Really, Fn equals mg. This is equal to mgs. Masses cancel out as they should, right? This is another situation, right? If normal force, gravity, and friction are the only forces, mass will not matter, which is good because otherwise you'd need to bank the, you need to have a different substance for each mass of person. And we actually do this, you get coefficient of static friction is equal to 0.64. Okay, and which is less than what you would need to, what rubber would be on a track, right? Which is probably close to 1. So that's the good news. All right, example 2. You're on a carnival ride. So this is a vertical carnival ride, right? And this is, I'm envisioning the one where like you like are on this like thing that goes around, right? On the, like it's got little wheels, and it goes around, or probably not really wheels, but you're down here, right? You're at the very bottom. And I want you to know, how heavy do you feel? So that's how heavy do you feel, right? This is, I want to know what the normal force is. Okay, so I'm at the bottom here. What forces do I have on me? I have a normal force up and the force of gravity down. So F net is equal to normal force minus Fg. But the thing is, F net is not 0 because I'm moving in this circle, right? So I've got m v squared over r is equal to normal force minus force of gravity. I start plugging things in. I have 60 times 10 squared over my radius of 8 is equal to normal force minus 60 times 9.8. If I solve this, I get a normal force is equal to 1338. Okay. Now, this is actually a fair bit, because think about Fg. Fg is just 588 here. So you're over twice. You feel over twice as heavy at the bottom of this as you would normally. Okay. All right. That's kind of weird to imagine, but we've all been there in like a tight turn where you feel like you're getting pushed down in your seat. That's the feeling. You're feeling heavier. That feeling that you're getting pushed down in your seat while you're riding a ride, you're feeling heavier. Humans, by the way, on a lot of roller coasters, they get up to, this is about 2 and a little bit times the force of gravity, which means it's about 2 point something G's. Whatever this is, 1338 over 588 is approximately 2 point, I'm going to say 2.2? Yeah, 2.2-ish, okay? The 2.2. So you're feeling about 2.2 G's on this. Humans, like on a big roller coaster, you might hit 5 or 6 G's just for a moment. 4 is pretty safe. 5 and 6 is a little bit like on the ones where it's like, don't go on this unless if you have like low pressure. 5 or 6 is totally, you might get 5 or 6 on those, but 4 is sort of like normal maximum. So this is really not that much, at least for a moment. You wouldn't want to do this for a long time, but 2.2 G's for a moment just at that bottom is totally fine. Okay. All right. One more. We've got a ball hanging on a 2-meter long string from the ceiling. This problem is what looks super simple, but it's actually super complicated. Or at least like interesting, maybe not complicated. So we got the string, we got this ball right here. And I want to know what this theta is. This is 2 meters long. Oh, I did some bad math. Oh, I did some bad math. Oh, that's so unfortunate. Ugh. Sorry, I'm going to change this slightly. And we're only going to be able to do an approximation. But it's still fun. It's still a good problem. Alright, I apologize. I'm actually going to shrink this as well to 0.5 meters per second, just so it's a little bit more obvious. 0.5 meters per second. Alright. apologies about that. I realized the math I was doing was a little bit shady. I made an approximation that isn't obvious. Okay, anyways, so we got what forces on this ball? We got Fg, and we've got tension, right? And then we've got the acceleration, right, towards the middle. So if we were to set this up, we would say that F net horizontal is equal to tension times cosine, oh, nope, it's not cosine, sine, opposite, right? Sine of theta, right? And this is equal to mv squared over r is equal to t sine theta. Huh? All right. We also know that sine theta is equal to, oh wait, hang on, this doesn't have an approximation. We good. What am I talking about? Sine theta is also equal to r over 2. Right? Theta's here. This is r. It's 2 because the tension has to be exactly at the same angle, right, as the string. So this is tension, right? I've got F tension vertical and F tension horizontal. And this is theta here. Oh, we're all good. I don't know why I was worried. No approximations. This is mv squared over r equals t times r over 2. Okay, so now I got to deal with this tension thing. Okay. Oh my. Maybe I'm wrong. I'm wrong. My math is all sketched out here. Oh, no, I'm back. I'm wrong. There's still a little sketchiness here. Okay, sorry. I'm going to go backwards here. This tension, right? So if you look at, sorry. All that. All right, so we're back here. So sine of r, this is true, r over 2. But when we look at tension, or F net vertical is equal to tension vertical minus Fg. And this is 0, right? It's not, no acceleration vertically. Tension vertical, or tension times cosine of theta minus Fg. So tension is equal to mg over cosine theta. If I plug that in, I get mv squared over r equals tension sine theta, not tension anymore, mg sine theta over cosine theta, which is mg tangent theta. So if we assume theta is small, then mv squared over r is equal to mg sine theta, because tangent of theta and sine theta are pretty close, which is equal to mg r over 2. And now we have a little math we can do. Masses cancel out, and I get v squared, 0.5 squared, which is 0.25. 0.25 over r equals 4.9 times r. So we get r squared equals 0.25 over 4.9, which, if I've done my math right, which is questionable, but not, no, I'm going to have to redo it because I did change something here when I fixed it. Okay, I did change something here. So bear with me a half second. 0.25 over 4.9. 451. 5 is, and this r is equal to 0.226. And if you actually look at that, what's that angle? Okay, what is that angle? Does this satisfy the small angle approximation? So we're saying that sine of theta is equal to 0.226 over 2. So that means, what's theta? Arc sine of 0.226 over 2. That's 6.5 degrees. Okay, so that's probably a safe assumption. Apologies for kind of garbling that one, messing it up. All right, so here's the deal. Bottom line for this. Set up your force diagram. Whatever direction the object is accelerating, in other words, towards this, whatever direction is towards the center of the circle, that F net is mv squared over r. Solve like you normally would.